Have you ever seen one of those massive container ships just gliding across the water and wondered how on earth it stays afloat? Well, the physics gets even more interesting when you find out they don't actually float the same way everywhere. Today, we're going to dive into the science that lets these giants navigate all the world's waters, from rivers to oceans. So let's get right to it with the big question. Why does the exact same ship sit higher up in the ocean than it does in a freshwater river? It seems kind of backwards, doesn't it? But it turns out the answer comes down to one simple but crucial difference in the water itself. Okay, first up, let's get our terms straight so we're all on the same page. The key word here is draft. When you hear that, all it means is how deep the ship is sitting in the water. It's just the measurement from where the water level is right down to the very bottom of the ship's hull. And right next to draft, you've got displacement. Now this is where the real magic happens, thanks to good old Archimedes. Displacement is the weight of the water that a ship pushes out of the way. And here's the cool part. That weight is exactly equal to the total weight of the ship. So from now on, when you hear displacement, just think ship's weight. Simple as that. All right, now that we've got those two key terms down, let's tackle our first puzzle. What happens when a ship's weight, its displacement, doesn't change at all, but the water it's floating in does? You know, like when it sails from a river out into the big wide ocean. So check this out. This image shows the whole principle perfectly. For just a second, ignore all the numbers and just look at the pictures. On the left, you've got our ship in freshwater, and it's sitting pretty low. But on the right, that same exact ship in saltwater is floating noticeably higher. So, what gives?
And here's the secret ingredient, density. See, not all water is created equal. Thanks to all that dissolved salt, ocean water is about 2.5% denser than the fresh water you'll find in a lake or a river. And that tiny difference, it changes everything.
So here it is, the golden rule for this entire topic. Denser water gives more of an upward push. It has more buoyant force. You can think of it as being stronger water. It's just better at holding things up. And because that salt water is pushing up harder, the ship doesn't have to sink as deep to stay afloat. It can ride higher, which means its drag gets smaller. Now, to really see how the math on this works, let's do a little thought experiment. We're going to forget about all those sleek, curved hulls on real ships for a moment, and we're just going to imagine a simple, theoretical, box-shaped vessel. It just makes the numbers way easier to see. And we can actually calculate this change pretty easily using this formula, which is basically just a ratio of the two water densities. We can see exactly what happens. So if our box ship starts with a draft of 2.1 meters in some less dense dock water, a quick calculation shows that when it hits the denser seawater, its new draft becomes 2.09 meters. It literally rises up in the water by a whole centimeter. Okay, so that's what happens naturally when a ship just does its thing. But what if you're facing a different kind of problem? What if you actually need to keep the draft exactly the same when you move from one type of water to another? Well, if you want to keep that draft perfectly level, you've got to play with the ship's weight. Take a look at the diagram. To force that ship to sit at the same depth in the salt water on the right, which remember is pushing up harder, you have to push it down. So how do you do that? You add more weight. You can actually load more cargo onto the ship, making it heavier, and it will float at the exact same level. And this right here is a huge deal for the shipping industry. Moving from a freshwater port out to the denser ocean means you can legally and safely pile on more cargo without making the ship sink any lower. We're not just talking physics here, we're talking about a direct economic advantage. But of course, this street goes both ways, and this is just as important for safety. This calculation shows what happens when a ship comes from the ocean into a less dense harbor. To keep from sinking too low and maybe hitting the bottom, the ship has to get lighter. And in this case, it's got to get rid of over 106 tons of weight. That could be cargo or ballast water, just to keep that same safe draft. Okay, so we've been playing around with these perfect, simple boxes, but you and I both know that's not what real ships look like. They have all these complicated, curved hulls, which means our simple box math just won't cut it. So how do real captains and naval architects deal with this every day? Well, they have a really clever shortcut. It's a pre-calculated number called the freshwater allowance, or FWA for short. Honestly, the best way to think of it is as a custom cheat sheet for each and every ship. It tells the captain exactly how many millimeters their ship will rise or sink when moving between fresh and salt water. And you know what? All of this complex science, all these calculations, it all gets boiled down to this one simple, elegant, and legally required marking that you'll see on the side of every big commercial ship. It's called the Plimsoll line or the load line. It's a brilliantly simple visual guide for a really complex physics problem. A captain loading cargo in a freshwater port knows they can load that ship right up until the waterline hits that F mark for freshwater. And they can do it with total confidence because they know that as the ship travels out to sea, the denser salt water will lift it right up, causing it to rise until the waterline lines up perfectly with the S for summer saltwater. It's physics you can actually see. So let's tie this all together. What we've really seen are the two sides of the same coin for a ship's captain. You're either keeping the ship's weight the same and letting your draft change with the water, or you're changing the weight specifically to keep your draft exactly the same. Knowing how to handle both is absolutely key. And this chart here just nails it. It shows you the two logical paths a captain thinks through. Path 1 on the left, is my weight staying constant? Okay, then my draft is going to change. Path 2 on the right, do I need to keep my draft constant? All right, then my weight is what's going to have to change. So why does all this matter so much? Look, this isn't just some neat physics trivia. Getting this right is the absolute bedrock of global trade. It allows shipping companies to maximize the amount of cargo they carry on every single trip, all while making sure that vessels stay safe, stable, and perfectly legal. So the next time you see a ship, you'll understand those invisible forces of density at play. And it might get you thinking, that Plimsoll line also has marks for winter and tropical waters, and since we know that temperature also changes water density, well, how does that factor into the captain's math?